speaker. This is Dr. Deshmukh, Rohan Deshmukh. He's a aerospace engineer in the Atmospheric Flight and Entry Systems branch here at NASA Langley. And he's going to be talking to you about a technology called Aerocapture. It's a method of planetary orbit insertion. I think that's correct. So without further ado, please welcome Dr. Deshmukh.
Thanks, everyone. Everyone can hear me? Awesome. Matt, can you double check if make sure it's on the Zoom call? You can hear and see. Cool. All right, awesome. So as Matt said, I'm going to be giving you a brief overview of how to surf on a planet's atmosphere, but use that to orbit insert using Aerocapture. So before that, I'll talk a little bit about myself. So I've been working 3 years now in D205 with Analytic Mechanics Associates, primarily providing flight mechanics support for various flight projects that are there. There are a bunch of acronyms. It's NASA, so I added some listings down there. But I think one of the most proud moments I've had recently was the successful splashdown of Lofted, where I served as the flight mechanics lead for Lofted. And that's me down there during my NASA TV interview, which I had zero experience of being on a camera. So it was a cool experience, going through the training and, giving the interview, once everyone's all the hurrahs and everything went successful. So before that, I got my bachelor's in aerospace engineering from Georgia Tech, my master's and PhD from Purdue University. My advisor moved from Georgia Tech to Purdue, so that's how I ended up at Purdue. And while I was doing my master's, I was an intern in D205 for 3 years, working pretty much on Aerocapture. So my research interests are on Aeroassist, which I'll talk about if you guys aren't familiar with what Aeroassist is, entry, descent, and landing, which I'm assuming most of you guys hear because that's what Langley's pretty well known for, and space exploration systems. So presentation overview, I'll give a overview on atmospheric Aerocapture surfing 101, talk a little bit about trajectory modeling using Aerocapture, and give a overview of 2 simple cases that I've looked at with Aerocapture, particularly for Neptune Aerocapture in support of ice giants missions, and then some small satellite applications. And then I'll conclude this talk. So I do want to say that this is not a comprehensive lecture on Aerocapture. So I'm going to give you a high-level overview. You guys are eating. I don't want to bore you guys and put you to sleep because it's very easy for me to do that. So I'm trying not to do that. So I'll give you a high-level overview and then give you a general summary of what some of the key results we got out of some of the technical cases that we looked at. So for Aerocapture, we're going to go faster than that you hear there. But before that, let's first talk about orbit insertion methods. The idea of Aeroassist is we want to basically utilize the atmosphere of a planet to help us orbit insert. But before that, let's talk about what we currently use for orbit insertion. So the most commonly used method for orbit insertion about a planetary body is a fully propulsive method, where you approach the planet on a hyperbolic approach, or just think of it as on your interplanetary trajectory. Once you get close to the closest approach to the planet, you do an orbit insertion burn, which basically decreases your velocity. So think of that as a delta V, which you'll kind of hear me talk about a lot during the talk. And this delta V could be on the order of a few kilometers per second. So it's a pretty expensive burn that requires a lot of propellant. You do that burn, and then once you capture into your orbit, you then do a burn to basically clean up and get into your target orbit. So that's the general method that's used for main orbit insertion. So I listed here a few pros and cons. I actually took a lot of this from Michelle Monk's slides that are there, so a lot of the credit is to her. But in general, the key takeaway I wanted to stress about fully propulsive methods is depending on what planet you go to and what orbit you're trying to get to, that orbit insertion burn can be very expensive. So if we can utilize the planet's atmosphere to basically help us reduce that delta V, then that can help us save propellant. So in fact, there has been a concept that has looked at this and has actually done this in the past, which is known as aerobraking. So the idea of aerobraking is you still approach hyperbolically, you do an orbit insertion burn into a very elliptical orbit. So it's not, it's a little bit lower burn you do, but your orbit is going to enter the very upper parts of the atmosphere. So think of it as it's a hot summer day, you're going to the pool, but the pool is really cold. You're basically going to tiptoe into the pool as you go through. So that's what aerobraking, the analogy you're doing. You're tiptoeing into the atmosphere through gradual, many hundreds of drag passes until your orbit drops down to you reach your target orbit. Then once you're done there, you do the same thing as a fully propulsive, you clean it up, and then you reach your target orbit. So as you can probably tell, you know, here's some pros and cons. So first off, it's been flight proven at Venus and Neptune and Mars. So there's been missions, both NASA and ESA, that have actually used aerobraking to do orbit insertion in the sense of changing their orbit. But at the same time, one of the key drawbacks of it is it takes a lot of time to get from your initial orbit to your final orbit that you want to get to, and it requires a lot of passes. I was kind of exaggerating with the animation that it does take hundreds, if not thousands, of passes in order to reach your orbit, which will take time and cost money. So, what if we can combine the two and say, okay, I'm the kid in the summer running to the pool, and I belly flop in, just go straight into the water. So the analogy with Aerocapture is we just directly enter the atmosphere. We surf when instead of belly flopping straight down, we don't want to land. We want to basically surf the atmosphere and then exit the atmosphere on our desired orbit. And then from there, we then do a cleanup burn in order to reach our target orbit. So from this approach here, in order to do this, we need to have basically an aeroshell to protect us when we're doing Aerocapture, because of the fact that we're going very deep into the atmosphere and the heating environments won't basically your payload needs to be protected from the heating. So the pros of it is that it's a very quick maneuver. It can basically provide you with that large delta V change that you need, which can correlate to a very large propellant savings. But at the same time, it's this concept hasn't been flight proven formally in a flight demonstration for doing orbit insertion. So you might ask, why then should we do Aerocapture? What are the benefits that we get out of it? So Aerocapture is an enabling and enhancing orbit insertion technique for planets with an atmosphere. So it can provide us with that orbit insertion delta V that may not be otherwise conceivable with propulsive methods. So to motivate this sort of bullet a little bit more, I have a chart here that I took from that shows a series of interplanetary trajectories that are going to Neptune. Neptune is one of the ice giants, which is one of the highest priority science missions that the current planetary decadal survey has looked at. So on this chart here, you can see on the left there is a vertical bar that shows where the region of propulsive orbit insertion is feasible, and you can see that the cases there correlate to very long time of flight, and basically all the other cases that are to the right of it can't be conceived with with the propulsive orbit insertion. So that really limits the design space for a mission that can go to Uranus. Oh, sorry, that can go to Neptune. But if we look at it, some of these cases that are shown on the right, where we basically have, you can see where my cursor is, where we can see at arrival velocity of around 20 kilometers a second, we can get very low times of flight, which can be almost a double save, a reduction of 50% in the time of flight from Earth to Neptune. And these arrival velocities actually correlate to Aerocapture entry velocities that we've looked at. So the advantage that Aerocapture can provide to us is it can not only provide us with a reduction in interplanetary time of flight, but it can allow for flexibility in our mission timeline. Say there's a launch delay, or say there's some programmatic delays. Given that we have a huge space here of different trajectories, Aerocapture can provide us solutions throughout this entire space here, whereas for a fully propulsive mission, we may not be able to achieve that with the very small amounts of subsets of points there. So I'll give a brief overview of the historical development of Aerocapture. So the historical development stems from Aeroassist, which I kind of talked about in a few charts ago with aero braking and Aerocapture in this case. So this is a chart I took from a a, um, a journal article that kind of just shows some of the ideas that they were thinking of using Aerocapture. Some of the ideas back in the day were crazy. They wanted to do these huge plane changes by flying through the atmosphere. They wanted to basically capture from the capture into orbit from a moon return trajectory. But the general idea was they were thinking of using the atmosphere of Earth to basically capture a orbit, to capture a trajectory into orbit around Earth. So in fact, in the 1970s, there were concepts that were developed by NASA to use Aerocapture for crewed missions to Mars. Figure on the right shows an example of one of those concepts. And in fact, Aerocapture was even set as the baseline orbit insertion for the 2001 Mars Surveyor Program orbiter as the baseline orbit insertion. And there was a lot of analysis that was done into that. The figure on the right is just showing an example of some of the analysis that was done there. The unfortunate circumstances of the Mars Climate Orbiter derailed the applicability of Aerocapture for this mission. And subsequently, since then, Aerocapture hasn't been formally put on a mission to do orbit insertion with. However, there has been a lot of studies that are there in the literature that have looked at Aerocapture. One of the most comprehensive studies that NASA has done is a series of design reference missions that NASA conducted in 2004 for various planetary destinations: Venus, Mars, Titan, and Neptune, to name a few. So these studies looked at basically sizing a mission and basically utilizing Aerocapture in order to enable those missions. So the figure on the right shows an example of such configuration of a vehicle that they designed for Aerocapture for Neptune. You can see when you look at this figure, this doesn't look like a Mars Science Laboratory Aeroshell that you might be seeing. Instead, this looks like a very advanced, very slender ellipse sled. So in this study, they concluded that given their design, that they needed something with a higher lifted drag than our traditional rigid air shells. So keep that in mind as I'll go on later to talk about a case study where we actually look at seeing, can we use blunt body aeroshells with modern guidance and control, given that this study was done almost 20 years ago, and seeing, can we use those updates in this past 20 years to enable blunt body Aerocapture. So recently, there in 2019, there was a study from a variety of Aerocapture technologists that documented what is the current state of the art. So this was published in the Journal of Spacecraft and Rockets. If you guys are interested, I recommend looking at it. I wanted to take a few sort of key bullets that came out of that study. So one of them was that they concluded that there wasn't necessarily a need for a flight demonstration mission, but they did acknowledge that it would be beneficial to do one in order to prove, Aerocapture at the subsystem level. But they did conclude that the technology that we have for Aerocapture is ready for Mars, Venus, and Titan missions. However, for the Ice Giants mission, there might be needs for advanced guidance and control. So they wrote that, I didn't. So keep that. So that's why that motivated to use advanced guidance and control methods to relook at those design reference missions, which are these DRMs here. So there was a need. So they wanted to look at trade studies and design reference missions in order to further improve the technology requirements that are needed for Aerocapture. Basically saying, okay, what sort of vehicle do we need? What sort of lift to drag do we need? What sort of flight control do we need? And then also doing some beneficial risk mitigation activities were deemed as beneficial as well. So what I want to motivate this slide here is to basically show how similar an Aerocapture vehicle is to a traditional EDL vehicle that we've already looked at. So the figure on the left is just a simple CAD exploded view of Mars exploration rover. And I want to use this just to motivate an example of how similar an Aerocapture entry vehicle would be to an EDL vehicle that we are pretty familiar with. So this EDL vehicle has a parachute canister in order to help for entry, descent, and landing. For Aerocapture, we're not landing, so we don't necessarily need a parachute canister. We also don't necessarily, instead of having a lander, we have an orbiter that we have stowed there. Additionally, we don't have a descent thrusters to help us land. Instead, we can have RCS thrusters to help us guide our vehicle as we fly through the atmosphere or surf through the atmosphere in theme with this presentation. So in general, there's a lot of similarities that we have to EDL when it comes to the vehicle and Aeroshell design. In fact, a lot of the subsystem level and the technologies are shared between Aerocapture and EDL. Now, of course, there are some differences, right? Aerocapture is not exactly EDL in the sense that we're going to exit the atmosphere. There's different conditions that a guidance would target. And of course, you have to carry some propellant on board to do some propulsive burns that you wouldn't do for an EDL mission. But in general, what a lot of people have concluded is that EDL is an inherently harder problem than Aerocapture in the sense that EDL has more complex phases in its flight as compared to Aerocapture. So as a result of that, Aerocapture might be a more conceivable mission going forward with the given current state of the art that we have with our EDL technology. So I want to transition just a little bit to talk and give you guys a high-level summary on a flight mechanics perspective on Aerocapture. So first, we'll talk about the flight control, potential options for Aerocapture. So these can either be a lifting or ballistic flight control methods. And the way we can sort of model the amount of control that they have is either by how much lift to drag they can produce, L to D, or the amount of ballistic coefficient ratio, or how much the ballistic coefficient can change. So let's first start with the lifting vehicle. So on the bottom left is just a simple free body diagram of an aeroshell and the aerodynamic forces that can produce. So the first concept for a control method is called bank angle modulation, or BAM for short. So this uses the bank angle sigma, and this sigma is used to basically rotate the lift vector about the free stream velocity. So the best way to kind of think about this is think about the lift vector as a clock, and the bank angle as the angle that the clock is making as it moves from 12 o'clock. So if the lift vector is at 12 o'clock, the lift is up. If it's at 6 o'clock, it's down. So basically the idea is as we're flying, we're basically moving that lift vector and just basically steering it around to either go left to right and control how much we're going forward and backwards. Sorry, forward, up and down. So it's a coupled control that you have. And this control has been used in EDL missions like MSL and Mars 2020 for entry, descent, and landing. The next option is direct force control, which says, okay, let's try to use two independent controls to decouple that motion so that we can have basically motion that goes, in our downrange motion and then motion that goes in our cross range. So the angle of attack is used to control the lift to drag of the vehicle, and the side slip angle controls the lateral motion of the vehicle through the lateral force Q. So the next force option is drag modulation. So drag modulation is a relatively simplistic control, which is just controlling the drag force that the vehicle imparts as it flies through the atmosphere. So the idea here is to look at a morphable aeroshell where you can control the amount of that drag that the vehicle can produce by modulating the cone angle that aeroshell has. So if you start at a base ballistic coefficient, which ballistic coefficient ties to drag, then we can deflect the cone angle similar to opening and closing an umbrella to basically control how much the ballistic coefficient can change during flight. And the amount of the max and minimum will define our ballistic coefficient ratio. So next we'll talk about guidance algorithms. I won't give you a master class on guidance algorithms. I'll give you a brief low-level overview of it. The general idea of these algorithms, where the current state of the art is utilizing numerical predictor correctors, where the idea is we have known atmospheric flight equations of motion. So while we're flying through the atmosphere, we integrate those equations of motion to our terminal point, which is when we exit the atmosphere. And we then basically calculate what our objective function is. Say we want to reach a specific apoapsis. We then use the value there. We can calculate gradients and Jacobian matrices and use those in numerical control optimization in order to optimize our control input to tell us, okay, this is what we need right now as our control in order to reach our target. And then we can keep doing that as we fly through the atmosphere. So this is just a simple way, just a simple block diagram of it, the explanation I kind of gave in that. So I won't go too much into the explanation of this block diagram. So the last phase of the guidance, navigation, and control that I wanted to talk through is the approach navigation. So the approach navigation, think of this as the initial condition error that Aerocapture has. So we start from when we enter the atmosphere, and then we end when we exit it. So if, as we're approaching the planet, we can have maneuver execution errors, or we can have some orbit determination errors that are going to basically affect our initial entry conditions. So we want to basically assess what effect do those have on our Aerocapture trajectory. So kind of think of it in that abstract view. So the key parameter that we tie this to is the entry flight path angle. And what we can do is we can use this entry flight path angle and determine, given how much control we have in our vehicle, what is the corridor width that the vehicle has. And then what we can then do from using that corridor width is compare that against what our nav team might say, this is our flight path angle error. And the idea here is that, as the example, if our flight path angle is 0.51, that's shown here, the spread of this value is going to be 1 degree. So when we look at our design space for our corridor width, we basically want to be in this green shaded region where the corridor width is greater than 1. So the reason I want to show this is, as mission designers, we can use the idea of having uncertainty in our flight path angle and model that to a parameterized design space where we might say, okay, how much lift to drag do we need in our vehicle in order to overcome this? Or how much entry velocity do we need? If we enter at a lower entry velocity, we then might need a larger lift to drag. So the idea here is that as mission designers, we can sort of parameterize our design space and then use that in our sort of conceptual design analysis for Aerocapture vehicles. So when we do our simulation environments, we can sort of build our models by first modeling the planet itself. So we use an oblate spheroid planet. I won't go into too much details on that. And on the table I have here is just showing a comparison for some of the different planetary parameters. So each planet is going to be different. However, what I want to kind of talk through, which is not part of a model, is the escape velocity. So why is that important, Ron? You might ask. Why do you care about the escape velocity? So as I talked about, if some of you guys are familiar with orbital mechanics, if your velocity is higher than your escape velocity, then you're going to remain hyperbolic. In order to capture an orbit, your velocity has to be lower than that than the escape velocity. So you can kind of think of this as a rule of thumb in our trajectory design to say, are we captured into orbit? So we can also use this number and compare it to the velocity that we enter. So I was showing an example in the previous chart about having velocities on the order of 29 kilometers per second. So keep that number in mind and compare that to a escape velocity of 23.5. So what that tells us is that in order to capture an orbit, if we enter at 29, we have to dissipate at least around 6 to 7 kilometers per second of delta V. So you might look at that and say, wow, that amount of delta V is almost the same velocity as a satellite in low Earth orbit. And with that in mind. So you can imagine how much propellant, if you do a fully propulsive mission, you would need to carry and burn that in order to achieve the same amount of delta V. So with Aerocapture, we're basically dissipating all of that velocity as we fly through the atmosphere of the planet. Now, there's no free lunch, right? That velocity has to go into something, and that's going to go into our Aeroshell and the thermal protection system, which I won't cover in this talk in too much detail. So speaking of the atmosphere, we model our atmosphere using the Global Reference Atmosphere Model, GRAM, developed at NASA Marshall. And we use this as an engineering model to give us an idea of how the atmosphere of each of the planets look. So I have here a simple plot of basically the atmosphere profiles for a variety of the planets there. Some of the planets have more uncertainty with them, such as Neptune, where we want to account for that uncertainty when we do our analysis. But the idea here that I want to just kind of show is, and I want to, as the key takeaway is, each of the planets is unique in of itself. when it comes to things like the atmosphere. So the air capture performance and sort of the results that we get are going to have a destination dependence, given that they might have a different planetary gravity model and a different planetary atmosphere. So when we design our guidance algorithms, we have to make them robust to these variations in different environments. So while we fly through the atmosphere, we have to generate aerodynamic forces in order to control our vehicle during flight. So what I wanted to show here are just two plots, and the key takeaways I want to take from these plots are just to show how a ballistic vehicle might control itself during flight and how a lifting vehicle might control itself during flight. So a ballistic vehicle might modulate its cone angle to basically control the ballistic coefficient. So as it basically reduces its cone angle, so think of it as closing the umbrella, as the cone angle decreases, you can increase the ballistic coefficient during flight. So if you can modulate that back and forth, you can have basically control over a wide range of ballistic coefficients. Likewise, for a lifting vehicle, you can control your angle of attack alpha and your side slip angle beta in order to control the lift to drag that your vehicle produces to control your trajectory. So that's the key takeaway I wanted to show on this chart here. So when we put that all together, we can put it all together in sort of into a architecture in a closed loop form in order to simulate our trajectories. So the idea here is that we basically are taking our guidance model, which is our numerical predictor corrector, just think of that as our guidance, and we want to test how well does it perform as compared to the actual environments of the vehicle, actual environments that it's experiencing. So we simulate that actual environment by defining a truth model. Just think of it as this is the actual environment in our simulation, and our numerical predictor corrector is using basically an onboard knowledge of what it thinks the environment is. So think of it as an example, the NPC has some knowledge of the atmosphere, but in reality, we want to test to see what happens if the atmosphere is 50% higher or 50% lower. Can our vehicle steer and correct for that? That's the general idea of what we're trying to do here. So we run Monte Carlos to do this. This is the general traditional way we've done it. So we can apply things like initial condition error with the delivery state that I talked about. And then we can apply uncertainties to the truth model like the atmosphere, the density I was just giving as an example. So next I want to kind of transition into two case examples to kind of show some of the analysis results that we've looked at utilizing some of these models that we used for Aerocapture. So the first one I'm going to talk through is basically looking at Neptune Aerocapture. So the objective of this study was to basically assess what effect do different flight control methods have on the performance of Aerocapture at Neptune. So recall I talked about in the 2004 design reference mission that they developed a slender aeroshell that I kind of showed the picture there. But what we want to look at is, can we use new control methods and our new guidance methods to potentially enable aeroshells that we're a little bit more familiar with? You guys might have seen an aeroshell that looks like this. This is the Mars Science Laboratory. So we're trying to stay in the family of, we want to see basically if we can use the advancements that we've done over these past 20 years to enable some of these aeroshell concepts that we're a little bit more familiar with. So I'm going to show three different cases, and the sort of design of the experimental setup that we went through to look at it was similar to what was done in the 2004 study. So the first one we looked at is basically the reference case that they looked at. And before I kind of talk through it, I have a legend up here that I'll basically, some of the results are going to refer to. So what we looked at pretty much are two different lifting vehicles, whether they have bank angle or direct force control, with two different lift to drags to basically see what effect does increasing the lift to drag have. Say you increase your angle of attack a little bit more and get a little bit more lift to drag. Is that beneficial to it? The general idea is we wanted to see if really this 0.4 was sufficient enough for air capture. So keep in mind that the 2004 study was using a lift to drag of 0.8. So this is actually a 50% reduction in the LTD to see. Can we still get a similar performance result as them? And then we also introduced a drag modulation vehicle, a single case here, just to see how ballistic flight control can compare against lifting. So the chart on the left here is the reference case here. And I do apologize, it might be a little hard to read on the left side here, but I'll kind of talk through here. So this is just a comparison of showing plots of the parameter. Think of this parameter bias as how the atmosphere percentage is changing with respect to the nominal. So if we have the blue values are basically, think of them as below average, below than average density, and then the red ones are above more than average density. So we can use that to basically correlate and see what effect does atmospheric variation have on our performance results and compare them across the different flight controls. So we can see here that direct force control, even with the same lift to drag, it's generally able to reach our target, which is this black dashed line, much more accurately than the angle modulation. So that just shows visually that there is some performance gain with the new flight control method. But if we look at our drag modulation vehicle, we see all these starred cases here, which are correlating to a lot of these below than average atmospheres. And these are actually cases that still remain hyperbolic. And the reason for that is that the vehicle just doesn't have enough control to overcome a more than basically a very low density environment. So that's an important thing we look at that when we do the comparison between the two. You might say, okay, we could probably alleviate this by increasing this ballistic coefficient ratio. So that might be a way we can kind of go at seeing if we can get ballistic flight to get similar performance as direct force control. So just as a quick summary, this is just some of the, I just summarized the results that I have here. And here are some of the statistics we got out of here. The key takeaways from the results is that direct force control produces almost half the 99th percentile delta V. So that's that's a 50% reduction in the delta V, which will correlate to a around 50% reduction in power costs. So that's a huge advantage we get out of direct force control for Neptune Aerocapture mission. So the next case is kind of a stress case here. This is saying, given our current ground environment, what if we just stress the atmosphere to its maximum capability to see what happens to our results? So the results we get out of it, that we get from the results, is we do see that there are some cases that end up remaining hyperbolic. Even though it might seem like a lot, the percentage that this is occurring is generally less than like 5% of the cases. But it's still important to know and understand our sensitivities early on to basically understand that we do see a potential mitigation strategy here. If we increase our lift to drag, we can see the number of cases reduced. So we have an idea of ways in which we can look at mitigating this. There are other ways we can look at improving this. However, the poor drag modulation vehicle, unfortunately, you can see the rainbow, taste the rainbow. There are a lot of uncaptured cases there. So key takeaway here is that with this max atmosphere environment, we may need to have higher control authority in order to achieve our 100% capture success. But we do see some promising trends, like I was talking about, where if we increase our lift to drag, we can still keep close to 100% capture success. We don't have 100 yet, but we do see some trends and promising results. So then likewise, the second sensitivity we wanted to look at is what happens if our initial condition error increases. So let's say our delivery error increases. How does that affect the results? We can generally see here on this result that our lifting conditions are generally resilient to those changes. There are some cases here that show up, but generally speaking, it's pretty resilient. However, our drag modulation case, it's not resilient to it. So we know its sensitivities in the sense that it's very sensitive to delivery uncertainties and atmospheric uncertainties. So this is just a summary of the results. I won't go into too much detail there, but I'll kind of summarize the key takeaways from the case that we looked at for Neptune Aerocapture. So the first one is we showed that if we use modern guidance and control methods, we can enable Aerocapture at lower lift to drags, around lift to drag of 0.4 as compared to a value of 0.8. And this can potentially allow us to use heritage blunt body aeroshels that we are well and more familiar with. Additionally, we provided, in this case, a comparison of lifting and ballistic flight control, as this is something that is important for mission designers to understand. What are the advantages and disadvantages of utilizing a more simplistic method of control, whether it be using a ballistic control as compared to using a lifting? And then we looked at each of the comparison cases, and we got we basically determined our sensitivities for a Neptune mission being the atmosphere and our initial conditions being our delivery state as our key sensitivities for affecting our air capture performance. So I do want to keep in mind that I am currently working on a NASA early career initiative with some other fellow colleagues here at NASA Langley, where we're looking at Uranus Aerocapture. So the idea here is we want to basically apply a similar methodology for Uranus Aerocapture to give a complete set for the ice giants, both Neptune and Uranus, to basically better understand how air capture fits in. Okay, so the next case is going to be looking at small satellites. So most of you guys, I'm assuming, are pretty familiar with small satellites are, so I won't go into too much detail into the slide here. The general takeaway I wanted to talk through this is that there is a lot of investment that NASA has into putting small satellites into future missions, whether they're being put on as secondary payload missions and achieving interplanetary science missions with small satellites. So basically the challenge that small satellites have is they have a unique mass and volume constraints that affect the design of your air capture vehicle if air capture is to be conceived. But at the same point, we do have some preliminary missions that have supported entry, descent, and landing missions that utilize small satellites. So this is a picture of Marco, the CubeSat that supported basically providing EDL relay during InSight's entry, descent, and landing in 2018. And this was an interplanetary small satellite that went to Mars. Even though it didn't capture into orbit, it nonetheless was an interplanetary small sat. So it just gives an example illustration of the direction that NASA is pushing with small satellites. So how can we apply Aerocapture, or in general EDL technology, and apply it for small satellite missions? So deployable aeroshells, ones that can stow during launch and then basically deploy once in space, are well conceived for these small satellite missions that need to be stowed in these secondary payload containers. So there's a variety of options that we can use. We can utilize a mechanically deployed system like ADEPT. Think of this as the umbrella method, where you basically stow it in a very compact configuration and then you deploy it as such. Or you can use an inflatable concept like a hypersonic inflatable aerodynamic decelerator, like Lofted in this case, which basically inflates from a very compact design in order to provide that aeroshell design once in space. So we do have Shelly Mann in the back here, and I want to give her credit for a lot of the analysis that was done for this project that we worked on, trying to see if we can take the current Lofted aeroshell design and downscale it to a small sat. So I do encourage you to take a look at her paper that she actually presented at the Small Satellite Conference. But I'll give you just a brief overview of the idea that came out of it, that she was able to basically produce a downscaled version of a small sat HIAD configuration, which just stows into sort of this configuration, which is a CAD model, and then deploys as such like this, where you have this payload cylinder that houses your payload that you would deliver to orbit. So the different configurations that were achieved included a deployed diameter that goes from 1.5 meters to as high as 2.5 meters, which is a pretty large diameter that was able to stow into the secondary payload adapter dimensions. So for folks who are interested in some of the numbers, this is just an idea of what the mass of the aeroshell is, the area that it's able to achieve, and the ballistic coefficient. So in the paradigm of small satellites, given their small form nature, the domain in which we do EDL is in a domain in which the ballistic coefficient is much smaller than what we typically see with EDL missions. EDL missions, they might be on the order of 100 in the ballistic coefficient. So the analysis using these SmallSat HIAD designs, some air capture analysis was done. This was just to give a preliminary look into what performance would this SmallSat HIAD design have for an air capture mission. So I have here just a quick summary table of some of the results. So if you think as a SmallSat mission designer, we can basically achieve orbit from entry to exit on the order of a few minutes with air capture. Likewise, the amount of velocity that can be dissipated is on the order of kilometers per second. So imagine converting that amount of kilometers per second into propellant mass and then trying to put that onto a SmallSat that's constrained to like 180 to 300 kilograms. You wouldn't be able to conceive a mission. So what we're able to kind of show here is, with air capture, yes, we do have to have some cleanup burns that are needed there. But if we take that propellant, that delta V, put that into propellant, we can see that it's generally less than 10% of the entry mass fraction. It's a really small percentage that you need to allocate into propellant for air capture. So what that generally demonstrates is that for small satellite missions, that air capture could, one, enable a rapid orbit insertion for a small satellite mission. It can reduce the orbit insertion delta V requirements from the order of kilometers per second to the order of meters per second, which is a huge improvement in trying to enable these missions for interplanetary missions. And like I said, it accounts for less than 10% of the total white mass. Okay, so I know this was a kind of a bumpy ride during the atmospheric surfing. So I'll have just one more slide, if you guys bear with me as a concluding remark for this talk here. So in general, air capture technology, it shows very good promise for enabling space missions for a variety of mission sets, from discovery class missions that are going to the ice giants to small satellite missions. You can think of these, you can even pack these as like Uber rides, where you have a air capture vehicle that contains a bunch of small satellites inside of that payload fairing, and air capture is basically the Uber service that gets you into orbit, into your around whatever planet that you're interested in. There's a lot of the technology that Aerocapture shares with EDL, which is very complementary in basically providing a level of confidence in Aerocapture and its potential capabilities, despite it not being formally demonstrated in an actual environment. However, there are some ongoing efforts to try to see if we can do a technology demonstration. I won't talk about that there, but I just wanted to bring those up just to keep you guys aware. So lastly, the last remark I'll give is, as the current recent planetary decadal survey that came out last year places a high priority in the Ice Giants mission, such missions that go to either Uranus or Neptune, they may not be conceivable without Aerocapture. And that's the reason why Aerocapture in of itself is very important right now, in the sense that there is a potential tangible application that Aerocapture can be put into to enable a mission so that scientists can get their payload and we can go back to Uranus and Neptune. So with that, any questions?
Thank you very much. Just note we have about 15 minutes for Q&A. The only thing I ask is that there are microphones on each table. Please use that for the folks online.
And Matt, can you tell me if there are questions online? Yep.
So I had one question about the relative pros and cons of Aerocapture with respect to the direct propulsion entry.
Turn on the mic there. Choose button on the front. By the light.
There we go. Yeah.
NASA engineers is good.
So you were mentioning that one of the weaknesses of propulsive entry was the time lag involved in communicating with your satellite or whatever you're trying to enter. How is that being eliminated, I guess, in the Aerocapture implementation?
Yeah, so the time lag, so I did recycle these slides from Michelle Monk's thing, so I would defer to her, but I think to try to answer your question, Aerocapture wouldn't necessarily eliminate it because it's something that's universal with given how far our destination is. So say we go to the ice giants, there is basically going to be a time lag that goes from our basically comms transmission between the orbiter, that's the Aerocapture vehicle that's way out there, to Earth. So it's going to be inherent with pretty much all three of the applications, both for direct fully propulsive Aerocapture and air braking. To answer your question?
Yeah, thank you.
Mo?
Okay, hey Rohan, I enjoyed your presentation. One question, I noticed that the blunt bodies were the 70-degree traditional configurations. Oh, thank you. Is there a movement or is there an advantage or disadvantage at looking other cone angles for these blunt body shapes?
Yeah, so that's a pretty hot topic these days, cone angles with EDL missions. So to answer your question, I think that is a open question in the trade space of it. So a lot of this analysis was 3-off. So we don't include the rotational dynamics, which is an important factor that each of the different cone angles will have uniqueness of it. So incorporating that and looking at the different cone angles would also be something to kind of look at. But in addition to that, it can also affect the packing, looking at sort of volumetrically, if you want to pack all your science instruments into an Aeroshell, basically the cone angle itself can influence how much volume that you have to stow some of the more larger science instruments that you have in your Aeroshell.
Gotcha. And just to follow up on that, I'm not sure if you're allowed to answer this, but for the Uranus Aerocapture study you're doing, is the assumption currently to also be a 70-degree sphere cone?
Yep.
Okay, thanks.
Yeah, I wanted to ask about the uncertainty studies that you were doing. So it looked like you were just doing Monte Carlo simulations. So I guess I first wanted to ask, like, how many, like, what's the population of your studies, and also how many, how many parameters are there to be varied in that uncertainty study?
Yeah, so I will preface it with, so there's 8,000 cases that we run per Monte Carlo. And I will preface it that, given it's a 3-off, there's not a lot of parameters that are being dispersed as compared to a traditional EDL mission that might have more complicated systems. It's doing a 6-off. So to kind of give you an idea, it might be, as our dispersed inputs that go into our system, it might be probably no more than 10. And then, we then input those in, and then we look at the outputs when we run 8,000 Monte Carlo. So it's a very crude sort of uncertainty analysis that we're doing.
Okay.
Answer your question?
It does. Just to follow up on that, is there any talk about adding more robust UQ analysis to the studies?
Yeah. So to answer your question, yes, we haven't looked into that yet. I think the traditional Monte Carlo method is like the way which most folks go into, but I think that's something that's important to explore.
Thank you.
Thanks.
Yeah, I have a question, kind of a follow-up there. Oh, need to be closer. Okay. So it was around slide 10 specifically. So these capture rates can kind of be turned around into a probability of failure. Is there an acceptable probability of failure?
So it depends on who looks at this. If this is
sure, yeah.
So
yeah.
if this is Congress and they see it's not 100%.
Yeah, sure, right. But there's always a real probability of failure that underlines that.
Yeah. So to answer your question, we try to strive for 100%, but it is important to know that, because a lot of this is like pre-phase A analysis, that it's important that we understand our sensitivities, that we understand what are the key drivers that can basically, lead to these failed cases, and understand why. So the reason like I kind of added those contour plots is it's a kind of way to visualize the input and to see how does it correlate to those cases, in the sense that you could see for lower density environments as that input that correlates to hyperbolic cases. So we have an idea on what's causing it, and then we can come up with ways in which we can mitigate it.
Yeah, and there are also ways you can use to sort of guide those Monte Carlo samples toward regions of input space where you're more likely to fail. So you're being more economical. I don't know.
Yeah.
Could be an interesting kind of next step.
Yep. That's a great question. Thanks. Ben?
Hey, Ron, this is Ben Merrill. Could you go back to the chart with propellant mass fractions for the small sets? Yeah, I mean, obviously that's really exciting to see those kind of numbers. Do you guys have either top of your mind or maybe in the paper you mentioned a sense of what the real change between the systems required to do capture looks like? How to think about that comparison?
Yeah, so we don't have like a proper number to kind of give to you, because one of the biggest areas that, going forward in future work that we want to kind of look at is to basically model how much fraction does the thermal protection system take. Because with Aerocapture, basically the idea is you're taking a satellite, you're basically housing an aeroshell around it. So you're basically adding mass to the total entry. But then at the same point, you have a thermal protection system and all the other configurations there, and you have to make that entire package fit within the secondary payload adapter. So to kind of answer your question, I think that's something that we're looking at in future work.
Yeah, thank you.
Man, you're gonna butcher me with all these questions.
No, I'm just curious. Speaking of thermal protection systems, are there any pushes towards a particular TPS for Neptune or Uranus?
CPCO.
Okay, thanks.
But that doesn't mean that we're not looking at others.
Yeah, I've just got a completely different topic. I'm just curious, with most of the studies that you were doing for, say, Neptune, how narrow is the corridor on like initial entry conditions between full Aerocapture, what might be an EDL situation, and failure to capture, so back into hyperbolic orbit? Like, are we talking, how wide is the entry angle that you have there?
Yeah, so I'm gonna flip back a few charts. So I may not have explained this properly, but to directly answer your question, that's pretty much the corridor. So the idea of the corridor is this basically tells us how wide that space is.
Mm-hmm.
The idea we want to basically say is that if we want to say that, okay, if let's say the entry flight path angle, if that's much bigger than the space that we basically have that we can control now, then we know that there's going to be portions of it where it doesn't overlap, that it's going to fail because we don't have that control.
Okay. Yeah. So you've got half a degree to work with, it looks like.
Yeah, it's really small, like when you think about it, but yeah.
Yeah.
So I'm relatively new to NASA, but I came from doing guidance electronics for missile systems, like flying bricks, keeping the pointy end in the front kind of thing. As you've looked at some of these new control algorithms, what's your mechanism for being able to test? Is it just all mathematical modeling right now with your 3 degrees of freedom, changing the variables? Or is there some analog here that you would use to identify what that would look like?
Yeah.
Given specific, I mean, we could do lots of terrestrial testing here on missile systems, but how do you verify those models?
Yeah, that's actually an excellent question. So for a lot of the analysis we do for for planetary Aerocapture, a lot of it has pretty much been computer simulations. But at the same time, one of the advantages for doing a flight demonstration of Aerocapture is to exactly answer your question, in the sense that you can take your technology, scale it down to a mission that you can test at Earth. For an Earth, you can do like a lunar return and then do an Aerocapture with that to basically prove, some of the subsystem levels. Of course, we won't be able to hit velocities as high as 29 kilometers per second, but you can downscale it and then do an Earth demonstration mission. And one of the ways that you could do it on a lower, at a cheaper scale is with small satellite technology. So you can kind of take advantage of some of the technologies that we have that, that are being developed. You can put them together. There are a lot of, potential avenues in which you can do that. And Earth is definitely a good domain in which you can test all those subsystems out, see how they run, and basically, give a kind of a stamp of approval for Aerocapture.
So I guess the follow-up to that is, if you're running these small sats and are these algorithms more math intensive? Do they require different levels of processing capabilities than is currently available, or are they just different and new?
No. So the numerical predictor corrector I was talking to, so that actually that algorithm in of itself, integrating equations, motion, and then doing some optimization, that actually was on Artemis 1 with the FT1. So it's something in which our current capabilities we have that we can do it. But it is an important thing to consider, is to basically take and make our simulations as less, computational intensive as possible. But, given the track record of numerical predictor correctors and how they've have some promise with EDL missions, they're not exactly Aerocapture, but they're kind of in that same family, that there is, good confidence in that we have the technology to run our our GNC codes.
So the last part is for these small sats, does the protection, normally a small sat goes into orbit, doesn't have to go entry, descending, it doesn't have to pass through the atmosphere,
Yeah.
shock, vibe, thermal, does that fall completely on the burden of the thermal protection system? Or can we quantize what the additional cost would be to protect the electronics from those sorts of surfing that they would have just had normally just a back burn just to slow it down really quickly? Is there a difference in how we have to protect the electronics of the actual satellite itself for this type of orbital insertion?
Yeah, the answer to your question is yes, there would be. It's something we haven't looked at yet. This is kind of a high level studies and all, but it's something in which, when we look at sort of encapsulating the small satellite within a payload fairing, there's going to be things like thermal heating. So a lot of CFD can be looked into that, just to make sure that, that the backside, the aft side, you're not getting too much heat loads that go into it that wouldn't be affecting your your small satellites. And then of course, shock, vibrations, G loads, all that sort of stuff, because they're not being directly applied in those environments.
Actually, Rohan, if I could add to that, usually the Aerocapture loads would be less than the launch loads and less than the circularization burn by itself. So by using Aerocapture, you're probably reducing the environment.
Thanks, Robert.
All right, everybody, it's 12:30, so thank you very much.